wahrscheinlich gleich um 10. Achso, okay.
Okay, so then let's continue with essentially systems theory in the engineering sense. So we now established what sequences are, and the next thing that we want to introduce are discrete time systems. And you might have noticed that the term system comes up in different contexts. So this is now the engineering system context. And in engineering, the main or the fundamental idea is that a system is something where you can put in something, and the thing that you put in engineering is usually a sequence, so something extending over time, and then the system does something with that, and then you get something out. I think what engineers love is somehow these kind of notations. This is then the system, black box, whatever that means, and then there's some output. This is kind of the engineering visualization of the whole thing. From my perspective and from the mathematics perspective, of course, a system is, and the way that engineers talk about systems is essentially that it's a function. So there is, in general, there is no noise added. It's a little bit weird when engineers and also physicists start to talk about systems that add some noise and so on, because then they get a little bit lost from my perspective, because then it's not quite clear what they want to talk about and so on. But essentially they're just talking about probability theory then. But what we talk about now is the system viewpoint as a deterministic thing. So the basic system approach, for example, you put some audio signal, so audio signal, so a time series of audio things into some amplifier system, and then you look at the output, something like that. This is what engineers deal with, and for this they develop systems theory, and this systems theory exists in both continuous and discrete time. And when you look at interest to convolution and linear time invariant systems, also in fMRI, for example, in this Hansen chapter in the SPM book, which I reference here, it's often in continuous time. And this is a little bit annoying, because if you look at the SPM code and how design matrices are generated, this is all discrete. So you don't solve integrals, but you deal with summations. So this is why I decided here to focus on discrete time systems, so not continuous time systems, which essentially just replace integrals by summations, but then also need more indexing and so on. So so discrete time systems, because we are interested in the application to the formation of design matrices, and systems in the engineering sense. So what then is a system? From this kind of little intro, a system is a function, and here I call the system T for some reason, which takes an infinite sequence and can also take a finite sequence. Then this notation is not quite correct, and outputs an infinite sequence. So this notation here, r to the power of z. If you are in math, the sets of sequences, I think they usually have an L or something like that. So I'm viewing them more as vectors here, so r to the power of z instead of r to the power of 10 or something. I don't know. It's one way we can do it. I tried to avoid a little bit this kind of formal notation of sequence sets in analysis, because they then always come with norms and so on. Anyway, so essentially what this should mean is a set of sequences and the important thing is that they can be infinite. Can ultimately not be infinite. This way, it's basically emphasizing the infinite part, but it's just a system has as domain the sequences and as range the sequences. That's the main point. And you put in a sequence X, and the system transforms, and I think this is where the T comes from, because it's also a transform, transforms the input sequence to an output sequence, which, this written here is TX. And this is essentially it. So this is a system. It's just a function. So a system is a specific function, and the specificity of this function lies in the fact that it takes sequences as inputs and gives sequences as outputs. So one example, so to not leave it completely at this abstract level, is the accumulator system, evidence accumulator. So is this the drift diffusion model? No, this is not the drift diffusion model. I didn't think that any one of you would ask this, but if you are at a general cognitive neuroscience thing, people would first think that this is the drift evidence accumulator. It has nothing to do with it. Well, it has, but in some different way. Anyway, so as an example for a system, the accumulator system, so what is that? So the accumulator system is a function that takes infinite sequences as inputs and gives infinite sequences as outputs, because it's a system, and then maps an input sequence X to an output sequence TX, which we now also call Y. And then, because as you know, this is just function definition, one has to say a little bit more about what's going on. So what is going on with Y? Y is now the output sequence, and the important thing here is that the ith element of Y, so Yi, is given as the sum of all elements, or elements of this input sequence X up to I. Do this again. So what this means is, let's say you have an input sequence X. X that has entries 2, 1, -1, 2, and these are for, so I put the indices up here, so this would be, let's say, -1. Okay, let's assume that these are all 0 before, and it's a lot easier. So there are a lot of zeros, and then at -2, at -1 we have 2, at 0 we have 1, at 1 we have -1, at 2 we have 2, and then from 3 on we have again zeros. Yeah, so that's our input sequence. And now the question is, what is our output sequence? So we want to compute the Yi, and then of course it's clear that if all the elements up to -I being -2 are all 0, then of course the thing at -2, so -2, and this is our I, and -2 is still 0. What is then the entry of Y at index -1? And as you started, you can also go on. What is the entry at 0? Yeah. Yeah. and then 4 and 4 and 4, yeah, exactly. So this is how this system works. So it essentially, yeah, as it's defined here, adds all the numbers up to I. What I like about the system is that it's showing how the entries of the output sequence, so of Y, depend on the entire sequence X. Yeah? So it would be if one had something where the ith entry of Y depends only on the ith entry of X, then it looks fairly much like a general function. So if, let's say, yi is xi square or so, then the sequence character doesn't really, yeah, or this whole system's character doesn't really play much into it. So this is why I like this accumulator example for a system, because all these values in Y, they depend on the entire sequence of X, or let's say at least to all of the sequence of X up to the current index in Y. Of course, you can define also sequences that also depend on future things, although in general, a lot of the systems theory in engineering obviously only looks back into the past and yeah, has this kind of as a causal system. So because it doesn't know, if you look at this in an online or real-time environment, of course it doesn't know what the signal in like 10 seconds down the line will be. So it makes sense that a system uses everything that has happened as input and not what will happen as input. Although if you then have a system that looks at already acquired data, then of course it can also look at that. Anyway, little details, but this is from my perspective a good example for discrete time system, because it shows at least the past dependency. Okay, so this is an example for a system, and if there are no questions, then we go a little bit further in defining specific systems, because what we are mainly interested in are what is called LTI systems. So which are linear time invariant systems. Linear and time invariant systems. And the bottom line is that one can use this convolution approach for linear and time invariant systems, which means that if we assume that we can model the whole stimulation or experimental event, neural activity, hemodynamic activity, MR system as a linear time invariant system, then using the convolution approach is sensible. Or stated the other way around, if we use the convolution approach, we buy, or we implicitly we implicitly buy into the assumption that we can model the whole system that we are interested in as an LTI system. So we should know what LTI systems are. We actually looked at this in the other course a little bit informally. Does anyone remember that? There were slides on that. These are the slides that you all need to memorize for the oral exam. So. I mean, not only these slides, but all of them, all 250 or whatever, but specifically these as well. Does anyone remember what that roughly meant with the LTI system? Or does anyone remember maybe I can show you them. So just to make explicit that this is the same thing as what we do in the other course, but here we do it better. So what I mean is '21st century. Come on. what I mean on these slides exactly. So, does anyone remember what linearity and linear time invariant behavior meant? I mean, we discussed it previously. These are the slides that I refer to. No? Do you remember that you have seen these? Good. Then we keep it at that. Because we define it better anyway now. So, look, there we are. So, what we discussed there, namely that things are linear and that things are time invariant, we discuss now again, but with a better understanding of what sequences are and what systems are, because we just defined sequences and systems explicitly. So we first now define what a linear system is. And essentially, a linear system is just a linear function. So if you know what linear functions are, then you already know what a linear system is. Only that systems are, of course, specific functions because they take sequences, inputs and outputs. And linear systems are systems that are additive and homogeneous, which are just two further terms, additive and homogeneous. A system is said to be additive if the output in response to the sum of two sequences. So T is a system, so it's a function that takes sequences as input. Here the input sequence is given as the sum of two sequences, namely the sequences X and Y. And a system is additive if it holds that the output to the sum of these two sequences is the sum of the outputs to the individual sequences. Yeah, so try to be clear about what this means. So here's one sequence that goes in. Here's the output to this sequence X. Here's the, I always see my pointer, so that's why I'm always say here and you don't know where I'm pointing. Tx is the output to the sequence X, Ty is the output to the sequence Y, and the output to the sum of the sequence X plus the sequence Y is the sum of the outputs to the sequence X and the sequence Y. And homogeneity essentially means that the output to the scalar product of a sequence X and A being a scalar, which is again, of course, a sequence. So if you form a scalar product of a sequence, you get a sequence again, is the same as the product of the output of the system in response to the sequence X multiplied by the scalar. Yeah. So this is exactly the definition of linear functions, but we are dealing with specific functions here. That's the only kind of difference with respect to linear functions. Then one can show that linear systems fulfill what is called the superposition principle. This is kind of a little exercise in linear functions. So for it's actually an equivalence relationship. If you have a system for which the output to the input scalar product of sequence X plus scalar product of sequence Y with B, so sequence X with A and sequence B with Y, is this. Then the system is linear, or if the system is linear, then the superposition principle holds. So that's an equivalence relationship. It's fairly easy to show that, so let's briefly do it. Of course, so a little proof here. Let's say we start with the linear system, so we say the system is linear. Then then the system is additive. So because the system is additive, we definitely have this. And because the system is linear, it's also homogeneous. So we also have this. And then we have shown that the superposition principle holds. It's something that you always, sometimes people introduce linear systems using the superposition principle, so they start with this equation, and sometimes they introduce it with the additive and homogeneity thing, so they start with this and with this. I prefer actually to do it like this, as you've just seen, because it's simpler, but both exist. Yeah, so that's a linear system. So the output to the sum of an input is the sum of the outputs, and the output to the scalar multiple of an input is the scalar multiple of the output to the inputs. You know what this is, but this is the actual definition. Questions about linear systems right now? There is, and I think I skipped that. With the accumulator system, one can actually show that the accumulator system is linear, and there is a little proof on this in the handout, and I looked again at that over the Christmas break, and I hope that the indices and stuff are, let's say, 92% correct by now. So if you want to see an example how this of a linear system, then have a look at this accumulator system again. We leave it at this because it's just a linear function right now, and go on to talk about time invariant systems, because we also need that. Does anyone remember what time invariance meant in terms of when we discussed fMRI?
The signal is independent of where in the time series it is. So what is before and after? So what is before?
There are a lot of things that one can interpret from what you just said, and then it's not quite clear what you mean. So, because I would say it differently. Can you say that differently?
Just remember the slide which you showed us before. So that the time variant system would be that if there is one response, then it alters the response which is after it. That goes into the right direction, but it's not. It's a little bit too complicated. So essentially, time invariance just means that that you get the same response irrespective of when that happens. So if this is time, then if you have this input at this point in time, so let's say at minus 10 seconds or whatever that is, you get a response that looks like this. And if you have a time variant system, that could mean that if you have an input, let's say at 5 seconds, that looks like this. This would be a time variant system, but this has nothing to do necessarily that this thing alters this thing. That can be the case. And this is what we discussed with habituation, but the fundamental thing is only that the system changes its response behavior. And this can be due to the fact that there were previous responses. This is what we discussed with habituation, but the meaning of time invariance is just that it responds differently if the input is provided at a different time point. If a system is time invariant, then it would also create exactly the same response at 5 seconds. So essentially, a time invariant system means that it always, irrespective of when an input occurs, the output is the same. It's of course fairly simple to describe with these unit sample impulses. We can do that a little bit more formal, and this is what we have here. So system is time invariant. So again, we have a system that is just this specific function and maps x onto tx. Which we call y, and the system is time invariant if for x tilde, which is defined as xi minus j, which I guess we have to discuss briefly, with j in z, it holds that t x tilde, so if I now put in x tilde, then I get an output y tilde, and this y tilde is of the form yi minus j. So what's this with the I minus j? What's the interpretation of that? So if we have, let's say, the following, now maybe denoting this whole thing with stem plots, and we start with -1, 0, 1, 2, and we put in 1, 2, 3, 2. Then, so that is our x. -2, and then we have 0 and 0 here. Then our x tilde, so that is our x. Our x tilde for, let's say, j being 2 is defined as follows. So what I think what this is supposed to mean is that if we have our x tilde I, we compute this from the sequence x, and we take the element xi minus 2. So in this case, so minus j, in this case minus 2. So then let's try that. So -2, -1, 0, 1, 2, 3. Then we also need 4 and 5, I guess. So for our x tilde, I being -2, we should take our x -2, -2, so -4. And for simplicity, we assume that everything that is outside of this -1 to 2 range is 0. So we have a 0 there. Let's make this blue. That's a 0. X tilde -1 is x -3, so that's 0. X tilde I 0 is -2 in x, so that's again 0. And then x tilde 1 is -1 in x, so that's, maybe we need some marks also here. So that's our 1.
So that's this thing here. Then our x tilde 2 is our x 0, so that's 2. Our x tilde 3 is x1, so that's 3. And then the 4, I mean, now it's fairly obvious to see what's happening. And then we have zeros here again. So this is this interpretation of shifting things. And this is, again, what will confuse me until I lie on my deathbed, that the minus shifts things to the right, which is just so counterintuitive. But it's once you do it, it makes sense. So it's a shift to the right. And the point is that if we now make this maybe in a little more simpler form, if we have, we could have this as an input to the system, but we of course also could have this as an input. So let's say we have -1, 0, 1, 2, 3, 4, and now I'm freestyling a bit, but it works. So we have this as an input, and we get this as an output. So this is now our y. Then if we now define an x tilde by shifting this, let's say by 2, exactly, so we shift it here, then the condition says that we get this as an output. So what you see is exactly what we discussed here already, that if you put in the input at a given time index, you get exactly the same output, but shifted. I mean, it's really simple. The idea is really simple. So whenever you put in the same input in time, you get the same output, but shifted in time. That's what a time invariant system means, but it's not necessarily completely easy to see that this is encoded in this little sentence here. That's what I'm trying. Aline, what is not clear? You look a little bit critical.
Yeah, I don't understand the notation with the tilde.
That's just, so the tilde, the important thing about the tilde is not so much the tilde, but the definition that, yeah, it's a little bit, maybe it's better to actually write it like this. So x tilde is, so I think it would be better to write it like this. X tilde is also a sequence, and it has these elements xi tilde, and these elements xi tilde, they are defined as the elements xi, so without the tilde, minus j. So that, I think, makes it a little bit clearer. So the ith element of x tilde is the xi minus jth element of x.
Okay, so the tilde basically means that it's just like a shifted copy of the actual value.
Yeah, so the tilde is just, one could also call that a or y or whatever, but yeah, it's, the idea is that it's, as you said, it's a shifted copy of the x. And I think it's a little bit better to include the x tilde here. Yeah. But this is what a time invariant system means. So intuitively, it just means regardless of the exact time point when you put in a given sequence, you get the same output, which of course means that the system is not changing over time. So of course, this is quite a strong condition. And if you think about biological systems, maybe even yourself today, I don't know, you can think of all sorts of things. You can think in terms of your knowledge. So if you now get asked a question, you give a different answer than you gave 2 years ago. You can also think about your alcohol metabolism, so that you feel one day after drinking, you feel worse than you felt when you were 20, but you are all 20. Anyway, so biological systems are usually not time invariant. That's what I'm trying to say. So time invariance is quite a strong condition. One can also say, also show that the accumulator system is time invariant they are actually this morning put in some correction of the indices. So if you have the script how it was there until yesterday, maybe look at the updated copy at one point or correct it yourself. That's a little bit of a index error. Okay, so why did we talk about sequences, systems, linear and time invariant systems? Because we want to talk about convolution. Other questions about linear time invariant systems right now? So maybe have a look again at the definition of a time invariant system, how it works, but I think with the example we made it quite clear. So why did we talk about the whole thing? Because I want to talk, and you need to know about convolution, and specifically the convolution theory. Before we can talk about the convolution theorem, we need one more entity, namely what is called the impulse response function of a system. So the impulse response function of a system is just the output sequence of a system for the unit sample sequence input sequence. And because I defined, as you remember, the unit sample sequences as not only one, which is usually the one that has k equals 0, so which has a 1 at 0 and 0 everywhere else. That's a question.
Sorry, we just talked about the thing before about this time invariance, just with this shifting. Isn't it in the on the left side when we were talking about I minus j?
No, we did it, and we saw that it shifts it to the right side.
Yeah, but we got confused again.
Yeah, so maybe clarify. It's a good exercise. Clarify that for yourself. It always confuses me, but if one does it, it's the same thing as if you have a function x, and for example this gives x squared, and then you do fx minus 2. It shifts it to the right, and that's confusing because one always has associated shifts to the left. But if one then does it, like we just did it, you can also watch the video again, then it shifts it to the right, and you see that. So watch the video again once it's online, and then create an example for yourself and see that it shifts it to the right. But on the other hand, you can also, if you're not happy, these are always this to the left, to the right, plus or minus, and so on. The important thing is more that it shifts it. And it shifts it to the right, but the important thing that it shifts it. And the most important thing is that it doesn't matter whether it's shifted or not for the time invariant system. Okay, coming back to convolution theory and introducing the impulse response function of a system. So we discussed today previously the kth unit sample sequence. An important example, of course, is the 0th unit sample sequence, which has this 1 at 0 and 0s everywhere else. Now, the impulse response function of a system, or better, the kth, what is this? Interesting. The kth impulse response function of a system is the output sequence of the system to the input sequence being the kth impulse response function. Being the kth unit sample sequence. So it's easier to write this down than to say it. That's what I mean. This doesn't go away anymore. So the thing is, you have a system and you have a unit impulse response function, and you put in the unit impulse response function into the system. What you get out is called the impulse response function. So it's the response to an impulse, and by impulse, what is meant is a sequence which just has one entry being 1 at a specific point in time and zeros everywhere else. So exactly what we did here. So if you look at the thing that is black, so you forget about the blue one, there we just have one pulse. It's a unit sample sequence. We have this impulse and we get an output. So this is of course what the system does. And this output here, this is called the impulse response function. Of course, what we have in mind is that this is our visual stimulus, for example, and what we can record. No, it's gone. Remember, there was a delta here which didn't go away. Anyway, we observe the bolt signal, and we've seen that we observe this. So of course we want to, as the impulse response function of interest for our case, we will discuss the hemodynamic response function. But in general terms, the impulse response function of a system is the response of the system to a unit sample sequence input. Yeah? So exactly this here. And I'm using an H for the impulse response function because we have in mind the hemodynamic response function. Yeah? So that's where the H comes from. So, but now we have everything together to at least introduce the convolution theorem, which we then, I think I want to put in the proof today and then look at examples next time. So, what does the convolution theorem say? The convolution theorem says if we have a system, and a system is a function that maps sequences onto sequences, if we have such a system with output y, and the system is linear and time invariant. So if these two conditions are met. Yeah, let's also include this. And H0 is the impulse response function of the system, is the of order 0, so it's the response of the system to the unit sample sequence delta 0. Yeah, if these three things are fulfilled. So we have a system, or 4 or whatever, we have a system, it's linear and it's time invariant, and we know the impulse response function. So we know the response of the system to the unit sample sequence. Then we can compute the output sequence y, so that's the output, for arbitrary input as follows. The ith element of y is given by this sum. We take the elements xk and we multiply them with the I minus kth element of the impulse response function of 0 order. So this is the I minus kth element of H0. This is kth element of X, and this is ith element of Y. So this is in a way pretty nice because we can characterize or we can. So what this allows us is to compute the response of a system for any input sequence. So whatever we put in, if we only know the impulse response function. Yeah, and we only need the impulse response function at time point 0, which actually follows from the time invariance, as we will see. So it's a fairly powerful in a way to deal with systems. So in engineering, the way this is used is that you characterize a system by its impulse response function. So you measure the response to an impulse. So for example, you put in electrical current of this kind of impulse behavior, you look at what the output is, and then you know the output to any input that you put into the system. Yeah, so you can predict the output to any system. And this sum here, this thing, this is called convolution or convolution sum. So in the convolution sum, you have the input sequence and you have the impulse response function. And I actually would like to look at examples of that next time and briefly guide you through the proof of this, just to make clear that this really this is only possible if the whole thing is linear and time invariant. So the proof basically goes in 2 stages. So the first thing is that we look at the output of the system to an arbitrary input sequence, and then we remember that we can write any sequence, and this is why we did this early on. We can write any sequence as a sum of impulse functions of different order. Remember that we looked at that at one point this morning. Then we know that the system is linear, so we can actually use the scalar or the homogeneity properties, so the scalar product properties. So we can, if you want, take we can use the homogeneity property and the additivity property. We actually use both here to get the system function onto the unit sample sequence. Yeah. So what is happening here is that first we can basically, because it's additive, we can apply t to all of these. So we can use t. This is one step that is not written down here explicitly. So we can first go here, and then we can use the homogeneity to go here. And then we already see that we can write the output of such a system as the infinite sum of the elements of the input sequence times the kth impulse response function. Yeah. And then the question is, what more can we do? And then the thing is that the kth impulse response function, because the system is time invariant, is exactly the same as the 0th impulse response function. So we can, instead of having it's the same, but it's shifted. So instead of having the k here, we can have the 0 here if we then look at the appropriate entry of this. So essentially what I mean is that if we want to compute yi based on this, we look at the ith entry of this sequence, which I'm trying to denote here by this I. So this is a sequence. So remember, this is an infinite sequence, and this is a scalar product. So here you have an infinite sequence, so like this infinite vector. And now we're looking at the ith entry of this, which is our yi. And this, of course, is given by so these are all these infinite sequences, and they are all shifted impulse response functions, because they have are based on different delta k's. So they hi. So they if we look at the entry, we see the ith entry of these kth impulse response functions. And now the ith entry of the kth impulse response function is actually the I minus kth entry of the zero order response function. So this is this proof that is on, here it's on pages 11 to 12, which is not, I mean, it's fairly trivial, but then one always has to really keep track of what these symbols mean. So, and then it's easiest actually, I found, if you visualize what these things are in terms of sequences, and that you perform operations on sequences. So, and these operations on sequences fulfill certain criteria. So here, because it's linear, you can get this infinite sum of scalar products of impulse response functions, which are all, if you think about this, responses to different unit sample sequences. So they are the same, they have the same form in terms of their how they look, but they are shifted in time. And then if one looks at the ith entry, then one of course taps into this sequence, looks at the ith entry, and because the system is time invariant, one might as well look at the shifted entry of the zeroth order rather than the the ith entry of the kth form. So this is one could, I don't know, that let me think whether I want to go over this again next week or not, because it's fairly important, because it shows how this convolution sum here only works and really needs these conditions. So it needs the linearity condition, it needs the time invariance condition, and it needs and it needs the impulse response function. That's clear, but it specifically needs the linearity and the time invariant condition. Otherwise, this convolution sum doesn't hold. So let me think over the week whether I want to go over the proof again or not, with a little bit more visualization maybe. The underlying message that I'm trying to convey here is that if people convolve their onset functions to generate regressors in fMRI, they implicitly assume that the whole system is linear and time invariant, and they buy into this whole system theory. And that's an assumption. That's basically what I'm trying to say. But I think I want to stop now because we're already running over. We definitely we go on with this and talking about finite impulse response functions next week, and maybe I can think of some visualization. So if you try to understand this proof, so I think it works now. There were times when it didn't really quite work because, of course, I get this from other books, and they are sometimes a little bit sloppy in terms of the entities they are dealing with, whether it's always the question, if you look into applied books, do they mean a function or do they mean a sequence versus do they mean a value of a function / an element of the sequence. And there a lot of books get actually quite sloppy, and then it gets really confusing. But I think I'm actually quite confident that the way I've written it now respects that the system works on sequences and not on elements of sequences. And yeah, so try to go over it again. In the end, what comes out is that you have this convolution sum, and you need to make some sense of this convolution sum as well. besides knowing that it only works for linear time invariant systems. And this is definitely what we will look at next time. Other questions right now already?
Can we also use it on EEG? Like, for example, if it's we have input and output, for example, that's this inverse problem and things like that when we have an input and want to predict output and how it doesn't apply for that.
Okay, so so it's an interesting question, but I think you mentioned different big fields of human culture when we talk about the inverse problem. So the forward inverse problem business doesn't need convolution necessarily. So there are things. So convolution and the forward inverse problem of EEG, it's best to keep them separate at first instance. But having said that, one can of course create regressors to predict EEG time series based on a convolution approach, and this is actually being done. If you do ERP analysis, you of course also have the idea of the impulse response functions of the EEG, which is an ERP, which is like a hemodynamic response function, but a lot shorter and hasn't anything to do with hemodynamics, but is still the response of the brain to an impulse. And you could analyze EEG data using a convolution approach. I think Vladimir Litvak actually implemented that for SPM at one point. It's usually not done because in the EEG world, people are more happy with event-related averaging and looking at the impulse response function per se. But to look at EEG from a linear time invariant systems perspective, of course you can do that. I'm not quite sure what you mean with the forward inverse. So I know what the forward and inverse problem are, but I don't know how it relates to
convolution. I'm trying to understand this, and like as far as I understood, we are trying to it's just that I started to think of it taking that if you can predict, yes. So can you?
But that's yeah. So. Predict, whenever you create a model, you can predict. So this is one way. So prediction, so to create predictive models, you don't need necessarily convolution for that. You can also exactly.
I mean, just like in this application, you can potentially use it.
You can always use everything for everything. Yes, it's not that commonly used. But so you would use it in EEG and the way you use in fMRI if you know the input sequence. So if you know something that you put into the person, so you have a temporal thing that extends over time. You know how the person, the EEG system, reacts to a single event. If you know that, then you can use the convolution approach to predict the EEG signal to this input sequence. So when you think about convolution, you should always think about sequences, putting temporal sequences into something and being able to predict the sequence of outputs or the output sequence based on the response to a single event. And in this sense, of course, one can use it for EEG. It's not that commonly used. That's what I'm trying to say. Yeah. Okay. Other questions?
I wanted to ask if you could explain again the G delta K.
This here.
How we're calculating delta.
Yeah. So what the delta is the unit sample sequence, which I introduced previously. So that's this delta Ki, which is 1 for K being I and 0 for K not being I. So these are these sequences that have a 1 somewhere and zeros everywhere else, and they have the 1 at K. So these are unit sample sequences, and these are the if you want, a unit sample sequence is showing bright visual stimulus to a person once in an fMRI scanner. And observing the, hemodynamic response would be the impulse response function. That's another question.
So following the time invariance condition, should the unit sample response be, or how do you call the delta? Should the delta be the same for every index I?
Should the delta be the same for every index I?
If the time invariance condition holds? So
No, the delta, so the time invariance talks about the age. That talks about the output sequence. So the time invariance means that the output so the time invariance just means that if you have the one at location 2, you get the output that suggestively looks like a hemodynamic response function starting at 2. If it's time invariant, the system, this means if you have another unit sample sequence that, for example, has its 1 here at 2, 3, 4, 5, 6, then the output you get is 2, 3, 4, 5, 6, no, 2, 3, 4, 5, 6. The output is the same as the output to the sequence at 2, but shifted by the same amount that the input here is shifted. So this is why I didn't get quite the question.
I have a lot of different deltas. I was confused. I think I understand. And this is, so this here, this black thing, to make this explicit, the black thing here, that would be, the black sequence here would be delta 2, and then the elements are these black dots. Yeah, and the blue peak here, of course, has also zeros everywhere, but that's delta 6, and it has a lot of entries. Yeah. Okay, but so we will continue with that, but let's stop here because we're running over time, and we also should talk about MR. Okay, but yeah. Have a look at that again, and next time let's see what we do. We definitely look at the examples of convolving. So we look at more closely at the response function that is of interest and that is used in fMRI, which is called the hemodynamic or the canonical hemodynamic response function. And we look a little bit of examples of what happens when you actually convolve different input sequences. And we talk about the finite impulse response function, definitely. Okay. Good, then let's have a break and start again at 20 past 10.